Log on, tune in, find out. Another good idea from Cambridge.
It's a great pleasure and honor to introduce Kari Astala, one of the world experts in quasi-conformal maps, who is going to, so for instance, he was famous in particular for solving the Calderon conjecture, one of the thought of as the biggest open problem in the field. And he's going to tell us about the role in inverse problems that quasi-conformal maps played in the solution of Calderon's problem. Kari.
Okay, thank you very much. And thank you very much for the invitation and for the possibility to visit here in this very lovely and interesting place. And also want to thank Tony Chen about the talk and getting us excited about quasi-conformal mappings, because it is really my main field. I'm not so much in inverse problems, more in quasi-conformal mappings. But I'm always looking for any applications that our field has. So inverse problem was one of the later important applications. So I think for a quasi-conformal person, I think the field has somehow like three phases. So one is this geometric part that Tony described, and that's used quite a lot in differential geometry and many other parts. And what I'll talk about is related to PDEs. So quasi-conformal mapping is a strong tool in PDEs. Of course, all these are related, but they're somehow different, little bit different direction. So with quasi-conformal mappings, we can create solutions to the PDEs even with very, very rough coefficients, where all other usual methods fail. And then the third phase of quasi-conformal mappings is the so-called holomorphic phase, holomorphic motions. And that was discovered in complex dynamics in the mid-80s. And Sullivan and Duary and others. And they realized that if you have any holomorphic complex dynamical system, and you perturb it holomorphically, you end up with quasi-conformal mappings. I mean, some kind of universal law. So these first two phases have now been used in inverse problems. So I hope that also the third, the holomorphic phase, will someday be used in the inverse problems. So, but that's for the future. And so I'll talk about my talk will be very mathematical. Mathematical point of view, and I'll describe some kind of overview of the two-dimensional Calderon problem and what is known about it and what kind of reconstruction algorithms it gives and so on. But before I start the real talk, we were discussing with Tony over the break, and one question that came in the previous talk was that why do you use conformal maps, or why quasi-conformal? Why not like this area preserving maps? And then so for quasi-conformal person, it's not so important that the quasi-conformal mappings they preserve angles or almost preserve angles. It's important they preserve shape. A conformal map, it takes a circle to a circle. A quasi-conformal map takes a disk to almost a disk. So, and I think this kind of property that shape is preserved. The size is not. The conformal map can take a small disk to a very big disk, but because the shape is preserved, and the human eye recognizes shapes much easier than many other objects. So maybe that's the reason why the conformal quasi-conformal mappings are so useful. If you use area preserving mappings, you can shapes get very easily distorted so that they are not so easily recognized. And this kind of rigidity in quasi-conformal geometry, that's somehow typical. It's also part of this holomorphic dynamics and holomorphic motions that I discussed earlier. But that's another story. So I just wanted to give my interpretation why these maps are useful. Okay, so what we'll be talking about is okay, sorry. forgot to introduce my colleagues, and few of them are here, and somebody he was here, Lassi and Matti are here, somebody was, Alan, he's a specialist in numerics and computer implementation, and I don't know, was Jennifer here earlier? Or?
Yes.
Okay, so the whole crowd is now at present. So what I talk about is the Calderon's problem on electric impedance tomography. So it's a problem that if you measure you do some electric measurements on the surface of a body, question is that can you determine the conductive structure inside? And this of course it's a very useful method if you can do it, and it has applications in many different medical situations. But what makes it so interesting for mathematicians is that it has an exact, clear mathematical formulation. Namely, the current satisfies this continuity equation inside the body. On the boundary, the Dirichlet boundary values is the potential, and the Neumann boundary values is the current. And then to know the boundary measurements means the same as determine the operator from the potential to the normal derivative, so the Dirichlet to Neumann or the current voltage pair measurements. And the question is, if you know this on the boundary, can we determine the structure inside? And what is so special here is that in 2 dimensions the problem can be completely solved. There's a long history, but I'll little bit mention about the history later. But there's many developments before us. But a few years ago with Lassi, we were able to show that if you have any non-smooth, any coefficient, so it doesn't have to be continuous, it doesn't have any differentiability properties. So we are somehow in the physically important case where we have real conductivities. So we are able to show that if the boundary measurements give the same result for two conductivities, then the conductivity must be the same inside the body. And then we did this for the isotropic conductivity, and later with Matti and Lassi we did it corresponding part for the non-isotropic case, and I'll little bit mention about that later. But my main point is that I will describe the reconstruction algorithm based on this result and the proof for the result. And if there's time, I'll describe something about the mathematics behind it and also some further developments. So, when did I start? 13, okay, thanks.
13 plus 45.
Okay, thanks. The stuff. Okay, so what are all these electric impedance tomography results based on, or the solution to Calderon problem? They are all based on the use of suitable family of solutions to the conductivity equation. And I will only describe or discuss the complex geometric optics solutions, which are solutions to the equation so that they behave like exponentials at the infinity. So one should think this as kind of Fourier basis related to the conductivity equation. And using these solutions, the first results were done by Sylvester and Ullmann, which for smooth sigma, and in higher dimensions, 3 dimensions and higher, they showed that the Dirichlet-Neumann operator determines the conductivity. So in their method, because you can, if your sigma is smooth, you can differentiate this out and relate this to a Schrödinger equation. And then using the ideas from Schrödinger equation, Ullmann and Sylvester proved the result. Then Nachmann prove the result in 2D using also the complex geometry optic solutions, and then ideas from integrable systems and the so-called D-bar-K equation, which I'll also describe a little bit later. Then Brown and Ullman had C1 result, so Nachman was C2, and then there are many other developments, and nowadays there's also other solutions to the conductive equation, the so-called Karman-Weight cases, and one replaces the exponential by more general object. Recently, Buchheim proved it in 2 dimensions. Solved the Calderon problem for the Schrödinger equation by using different weight, but still a little bit of the same spirit. Okay, so what is the role of quasi-conformal mappings in this setup? Well, we are supposed to find these solutions and then apply them. So how to find them solutions? If you have non-smooth coefficient, it's not so easy. And actually, the only way I know is to use the quasi-conformal mappings. So here the quasi-conformal mappings is a tool to solve PDEs. And how do the quasi-conformal mappings come here? Well, we just use the methods from complex analysis or the harmonic conjugate, also called, or you can also think it as a hot star operator. So we take the hot star operator in 2D, which you can represent by this matrix, and then you see that any solution to the conductive equation admits a conjugate through the hot star operation. And the pair U and V forms a mapping which is a quasi-conformal or quasi-regular mapping. That means it's locally quasi-conformal. Now, if you take any solution to the PDE, of course it doesn't have to be injective. Quasi-conformal mappings they preserve the local geometry, like Tony explained, but they are also injective. So not all mappings which satisfy this Peltrim equation, they are injective. So, but there's this so-called Stoyle factorization theorem that any solution to the equation is of the form, it's a composition of a holomorphic mapping and a quasi-conformal. Now holomorphic, they are easy or almost trivial, and the only difficult things are in this quasi-conformal part. So this is a very powerful tool to understand the PDEs, to use the equation and the Stoyle factorization. And what it also brings us is the topology. In 2 dimensions, the topology becomes important in the important tool in understanding the equation. Okay, and using these methods, we then show that for any k, any complex exponent k, you can find this complex geometry optic solution for the Peltrim equation, so with the right exponential asymptotics. And from this Peltrim equation solutions to this, from these quasi-regular mappings, then you can find the solution to the conductivity equation. Okay, and then the story begins. But also here in the proofs, we will use the quasi-conformal mappings in a very crucial way. Okay, and once this state is set up, then we will then I will then describe this reconstruction algorithm that we get from our proof. And this is our joint work with Jennifer Müller and then Samu Siltanen, Alan Perämäki and Lassi Päivärinta. And it turns out that once we do this reconstruction, so first of all, it has very good contrast resolution and good spatial correspondence. So I'll show pictures in a minute. It also applies to all non-smooth coefficients, so all physically relevant situations. It's non-iterative, and what's the crucial point of the argument is that we solve a PDE on the Fourier side. Now Fourier side meaning that remember that this complex geometry optic solutions, they were like exponential functions. So we have a Fourier space from there. And solving a PDE there gives, that's a crucial point of the argument. Then filtering on the Fourier side gives a regularization for the problem. And then just the last remark here that there's very sharp stability analysis by Ruiz and Klopp and Faraco. It shows that we have stability for, if you have a little bit Sobolev smoothness for the coefficients, then we get immediately the stability. So like characteristic functions of smooth sets, they satisfy this Sobolev condition. So there's a lot of discontinuous coefficients for which we have a very good understanding of the problem. Okay, so here are some pictures, our first pictures. So we have a conductivity, it is somehow like it should represent lungs, and here's I guess a heart. And then we produce the boundary data related to this conductivity, and then reconstruct from the boundary data with our method the conductivity inside. And then here the R reflects means the size of the disk on the Fourier side where we truncate the PDE. Here next is a picture with noise, so there's some percentage of error, but it's still quite reasonable. Okay, so to describe the algorithm, I will first need some tools from the complex geometry optic solutions. And there's one basic fact that Adrian brought to the inverse problems. It was first realized by Bills and Koihman in the integrable systems setting. And it's some of the crucial fact in 2D for this complex geometry optic solution, which somehow saves the whole situation. Namely, if you look at the solution to the conductivity equation with this exponential behavior, then we assume that sigma is already given on our given domain. Let's take it to disk. Outside we set sigma equal to 1, just for convenience. So outside disk we have harmonic functions. So they are sums of holomorphic and anti-holomorphic functions. And comparing their coefficients, we see that we have a special identity for the mapping. So when we derivate with respect to the k bar variable of the parameter, we can write this function as in terms of the conjugate of the original solution. And what is remarkable here is that this coefficient, so this works for at every particular point z. But what is remarkable is that the coefficient here is not depending on the z at all. And it's somehow unexpected result that this is true. Okay, so like I said, the Bills and Koihman, they first realized this in integrable systems, and then it has been a very useful tool, and after Adrian we also used the equation in a little bit implicit way, but I'll explain that a little bit later. Okay, but the point is that this coefficient, it comes from the solutions outside our domain, and therefore it can be determined by the Deligne-Neumann operator, so from the boundary data measurements. So we can really calculate this coefficient in terms of boundary measurements. And then we have a differential equation, so solving it, that should give the function, and from the function we get the coefficient. And this is actually, oh sorry, but Adrian's argument for smooth coefficient work. So I'll little bit describe this because I want to compare and okay with the rough situation, rough coefficient situation. So sorry. So in this case, for smooth coefficient, we multiply the the conductivity solution by the square root of the conductivity, and in this way we have a solution to the Schrödinger equation. And the asymptotics are still the same, because sigma or coefficient is equal to 1 outside the disk. Okay, and in the same way as for the harmonic functions or this conductivity equation, the Fourier asymptotics give us the Debye equation. There's exactly the same argument. And taking out this Fourier factor gives us the PD, this Calderon-analytic equation for the unknown coefficient mu. And then using the Schrödinger equation, Adrian showed that this Fourier, this perturb coefficient, it converges to constant 1 when the frequency goes to infinity. And this is enough enough information to solve the Calderon's problem, because now it turns out that when the Fourier coefficient, Fourier variable goes to 0, then in the limit we get the square root of the sigma. Why is this? Well, there are many proofs. So there's the original proof, but simple way is to use these complex geometry optic solutions. It is easy to see that they are equal to 1 when k is equal to 0, and there you get the result. And then this was implemented by Isaacson, Müller, and Siltanen. Okay, so this is very beautiful algorithm, and it works very, very nicely. So should we use this also? The proof use the smoothness, but should we use this also for rough or non-smooth conductivities? There have been experiments for this, but what is somehow the crucial point? Okay, we have these two requirements for the equation, and the first is this Debye equation, and the way we derived it can be done also in the rough coefficient case. So once you have the complex geometry optic solutions, then you have the Debye equation. That's no problem. But the real problem is the second condition. Do we have this? Okay, yes, thanks. So this should be, yes, exactly. This should be k equals to infinity. Okay, so we are looking at the high frequency asymptotics. So what is the high frequency asymptotics? And then using the Schrödinger equation, Adrian showed that they go to constant at high frequency, k equals to infinity. Okay, but how about for non-smooth coefficients? Do they still have the same asymptotics? Okay, why is this important? So now suppose it has some other asymptotics. Okay, we have still the equation, so then let's multiply it by some function so that we get the right asymptotics. Well, once we multiply it, then this second condition is destroyed. So you cannot anymore, if you somehow arbitrarily normalize the solution, then you cannot anymore recover the conductivity at the frequency 0. So you cannot choose the arbitrary asymptotic. So it's really important that we have this constant value at the high frequency limit. The question is, do we have the same for L infinity conductivities? This is if we have, then we can use the same algorithm and same approach. Now, to be honest, we don't know. So there's some experimental data. It shows that this coefficient seems to grow, but we don't have a mathematical proof. And this is some other missing pattern in this 2D electric impedance tomography setting. If you have the exact asymptotics of the for these complex geometry optic solutions for rough coefficient, then many other points would also be solved. So this is some of the remaining open questions. But somehow, okay, now this is some who draw this picture for the solution to the Peltrim equation. But by linear combinations of these, we get the solution to the Schrödinger equation, and they seem to be growing. At least they don't decay to zero as one would like to. So the question, okay, if you cannot use this, if you cannot use this Debye equation, what can we do? So what to do? Well, what we then decided to do, and okay, what turned out to be a different way, was to use the Debye equation to derive another equation in the Fourier side, which is somehow better for asymptotics, and then using this other equation, then one could save and reconstruct the conductivity. And this reconstruction strategy is as follows. So first we make an integral equation on the exterior of the domain, and then solve with this solve from this Dirichlet-Neumann operator the solution of the conductivity equation outside the disk. Then secondly, we use the PDE, which we call or the machinery using it, we call it transport matrix. And we transport the data outside the domain to the inside. And here the Debye equation is a crucial tool. And also we do some low-pass filtering, so that our coefficient, we have actually the Peltrim equation. So we have to get to control the asymptotics of the equation at infinity, we must truncate the coefficient, and that gives us the low-pass filtering. And then once we have the solutions inside the domain, then we can construct the. So once we have solution for the conductivity equation, then we have the solution for the Peltrim equation, and from there we get the conductivity by this simple algebra. And there's no problem here in taking the derivatives, because we have already taken the low-pass filter in the smoothing. So only ill-posedness is in this step 1. Okay, so let me briefly describe the steps. So remember the Peltrim equation. Okay, let's look at here. So if the coefficient nu is 0, our functions are holomorphic. So you should think nu as a complex structure. You are given a nu, so you are given a complex structure, so you need to find the mappings, mapping the original structure to this given one. And with the complex structure, you have many tools from complex analysis, all different operators and so on. So for instance, we have the so-called Riesz projection, which takes the mapping, cuts away the negative Fourier coefficients of a function. And there's a similar operation, of course, in other complex structures. That's one thing that we are using. The second is that the Dirichlet-Neumann operator is related to these complex structures. Because the conductivity, the hot star operation, it relates the solution to the conductivity equation to a conjugate. And this relative mapping to a conjugate, it's like harmonic conjugate. That relates us to the complex analysis. And it turns out the Dirichlet-Neumann operator is exactly the derivative of the so-called Hilbert transform in this new structure. And then the difference of the new structure and the old one, usual complex structure, is just a compact operator. And we get the Fredholm integral operator, integral equation, and solving this, we can find the complex geometric solutions inside. At least first on the boundary, and then from because they are analytic functions, then we can find the coefficients and determine the function in the whole domain. And the point is that only ill-posedness arises in this step, in this inverting the Fredholm operator. Okay, the next step is then, once we have the function outside, how to go inside. Well, here we first look at the solutions to the conductivity equation. Now omega 0 is a point outside the domain. And then we have to use, besides sigma, also the coefficient 1 over sigma. But the linear operators of these two coefficients are related, so that is no problem. And then what we are interested in is inside the domain, point Z, and we want to relate the values inside to the values outside. And we just take by linear algebra, we find some coefficients A and B. That is no problem. But the point is that now that we use the d bar k equation, it turns out that because all these conductivity equation solutions, they satisfy the same d bar k equation where the coefficient is independent of the space variable z. So when we take the d bar derivative, there are several terms cancelling, and what remains is the following equation involving the coefficients a and b. And it's another Beltram equation. So we can solve it, and then the coefficient, the Beltrami coefficient, it depends only on data outside the domain. So it depends only on the Dirichlet-Neumann operator. So it's something that we can calculate and then okay, numerical estimate. Secondly, we need some mathematical tools, mathematical results which say that these complex geometric optic solutions, they behave a little bit better than this error term in the complex geometric optic solution. It behaves a little bit better than the linear part in the exponential, and just that is required to differentiate these solutions. Now, the pictures I described show that this should go very quickly to 0, and in the Nachman case this was like 1 over k, this whole term. But what is really the right asymptotics? It is not known. But it's still enough data to be able to solve the equation we can solve the equation and then the coefficients a and b, and from there we determine the solution inside the domain. And then this is the result. Here we have looked at again some simulated situations where there's a small tumor inside the lung, and even in the pictures you don't see the difference, so the relative error is still visible. So there are many situations where you can use this. Okay, so here's another picture, and then what is somehow the missing part, or the next step, we should look at more difficult geometries to see really, I mean, what is the, we have not done yet the experimenting that what is really the high frequency asymptotics, so with very complicated geometry. So that is the next step. Okay, so now how many? I would 10 minutes. 8. Okay, very good. So okay, but I'm happy with 8.
Lassi will tell you when you're done.
No.
Okay.
Yeah, Lassi is tough. So, okay, so there are several generalizations, further developments, and I would like to a little bit describe this. And of course, time doesn't allow the whole development, but because somehow we have not yet seen how the quasi-conformal machinery arises, how it's used and applied. So I'll let a little bit describe that. And what we are looking at are these cloaking geometries and the limits between visibility and invisibility. So when you recall the proof I just described, we see that it didn't use many properties. It only used the fact that we have these complex geometry optic solutions and there's some control at the infinity. So it turns out that they are degenerate conductivities which have the same properties. We can still work with them. And what makes this especially interesting is the recent development in this invisibility cloaking studies. By changing the geometries, one builds this cloaking materials, and then this was one of the first one of the first pioneers in this field were Greenleaf, Lasses and Ullman, who produced the following example of a cloaking material. So what I would like to discuss is that how degenerate material can be in order this not to happen. So how degenerate material can be so that the Calderon's problem still works for it. Okay, so here we just describe how to change the geometry and how that changes the conductivities. And then here somehow the main, not the most general result, but the result that is most easier to remember. This is how you should think of the result. So it turns out that you can have some exponential integrable degeneration. So the degeneration is not very strong because it's still exponentially integrable. It turns out that if you have this exponential integrability and you have the coefficients determinants are bounded from above and below, then the Calderon problem still solves in the same way as for bounded coefficients. Now one can do a little bit better by looking at other examples, and then the best or the weakest or let's say the best example of singularity was by Ivanets and Martin, where they showed that if you have this condition on the condition on the exponential integrability, that it's a little bit more than linear, then you have counterexamples for then you have this blow-up phenomena, and then this gives counterexamples for the Dirichlet-Neumann, for the Calderon problem. So the most general result is that we can, if we have this exponential integrability where the integral condition is infinite, and we have this exponential integrability of the determinants, then we can find we can still solve the Calderon's problem. Earlier, I gave a talk about this topic like in Berkeley, but then we had only 2 exponentials. We realized in the process, now the paper is ready, and we realized that at one moment we need 1 more exponential. Of course, we conjecture that this is unnecessary, but also here, if you have new methods to control the high frequency asymptotics of the complex geometry optic solutions, I think that is the point to solve this, to get rid of this extra condition. But like I said, that is very much unknown. Okay, and then I have a couple of minutes, and here I would like to describe a little bit how to use quasi-conformal mappings. So I said all the time that these maps are used to construct these solutions, but how do we do it? And I am doing it in the degenerate case. So when the coefficients are not degenerately bounded away from 1, or this K distortion can be infinite at some point. Okay, so we are now in the, if our equation is not isotropic, then we need two Peltrami coefficients. Here we have other coefficient in front of the D bar, the DEF complex conjugate term in front of this complex conjugate term. And there's a more geometric way to look at this, is that mapping which satisfies this equation satisfies the distortion inequality, that the maximal derivative is controlled by this function times the minimal derivative at any point. So that says that the differential maps the circle to an ellipse, just like Tony described. But now the eccentricity of the ellipse is not bounded away from infinity. It's bounded by this constant k, and then it is not necessarily bounded. It can go to infinity at some point. And there was a big boost in the theory of these mappings, where you can have some degeneracies, but still control on the ellipticity. And that's now so theory of so-called mappings of finite distortion. Now, if you are not familiar with this Beltrami equation of the distortion, it's easy to visualize them by looking at just the conductivity equation. So all these quantities are related to each other by simple inequality. So this trace of the matrix, which just looks at the singular values of the matrix at the point Z, it's roughly the same as the distortion k of the mapping. It's roughly the same as this quantity. So if mu and nu are very close to 1, then this is very big, and then the singular values are also very big. So this is how you should visualize the conditions. Okay, and now using this machinery, we should then solve the conductivity equation with this exponential asymptotics. And here somehow the quasi-conformal machinery begins to work. The idea is that we don't look at this solution as a perturbation of the exponential term. We look at the phase term in the exponential, and look at what is the equation satisfied by that. And the reason is that if the phase term has, by our choice, this asymptotics, and so at infinity it is homeomorphic. So it's conformal, and therefore it's homeomorphic in the whole plane. And with homeomorphic mappings, we have much better control on the geometry. So the phase function satisfies the following inequality, and then here we have some estimates for it. Now, if we assume exponential integrability of the distortion of these trace terms, then we can bound the derivatives of the function in terms of the distortion and the Jacobian by the following inequality. And what the topology brings us is that this, because phi is a homeomorphism, this integral is bounded. The second is bounded by assumption. So we get that this kind of Orlich space regularity for the function phi. And that turns out that it's actually the right choice for the regularity, because it gives us modulus of continuity estimates, and there we can solve these degenerate equations, and you have the following result: that if you have the exponential condition for the singular values of the matrix, then we have the complex geometry optic solutions with this regularity. And you may still wonder why we have this strange Orlich norm, why not something else like L2? And I just point out that it's because we have to. So L2 is not true, and if you have W1Q space where Q is less than 2, then you have these cloaking counterexamples and things work out. So we are really forced to look at these different Orlich spaces, related to different conditions, and play with these. Okay, so I think I gave a little bit taste of what kind of quasi-conformal machinery has to be used, but I think I will stop here, and thank you.
Thanks very much. Questions? Bill.
So this is beautiful work, and it's wonderful how quasi-conformal maps come into the 2D case. Unfortunately, 2D EIT problems are very rarely useful. If people are two-dimensional, they've been squashed, they're already dead. And however, in geophysics, it's quite common that they lay out a single curve where they put the sources and detectors,
Mhm.
even though the domain is three-dimensional. And I just wondered if you had any thoughts of whether quasi-conformal maps might be applicable. So they make some kind of 2D approximation. They assume the conductivity is invariant in the direction normal to the curve they're measuring. So it may be a line and it's invariant in that direction.
Okay, so there's one somehow like
They're making
foliate
a
the
2D
space.
data on a
Yeah.
3D domain, essentially.
Yeah, so if you can somehow foliate the space with this 2D, and you possibly you can control these 2D geometries.
In fact, that's the most common case. I mean, all over the world, people do EIT like this
Okay.
on the Earth because it's cheaper to measure along one line.
Okay, so maybe we should then start to apply this and foliate. So I never studied this, but this is a very good idea.
Yes, okay.
Yeah, so you're trying to recover rough coefficient,
Yes, yes.
but you use low pass filter. All
Yes.
the information about the contrast, discontinuity are gone.
Okay, so of course we can try to take the filtering bigger and bigger.
But then
But-
it becomes very, very unstable, less and less stable.
No, I mean, it doesn't bring any unstability or impostance comes in this solution to boundary integral. But it's this calculation of the solution becomes more complicated because we are using this. Okay. I need one. We are using this equation. If this coefficient mu and u, if they are not compactly supported, suppose they in this k equation they are supported in the whole plane, and then usually you solve the equation, Bertram equation for compactly supported mu by some Neumann series development. But if mu doesn't have compact support, you cannot do this. You have to get some normal families results and so on, and then things. I mean that you can do. That you cannot implement numerically. So I don't think it produces instabilities, but it's some other solution. Solvability becomes more problematic when the truncation becomes
But your
bigger.
noise in your example is 0.01%, so it's very, very, very small.
Okay, so to be honest, I might be on this theoretical side, and Samu and Jennifer, they have done the numerical experiment. So I'm sure you're right, but I cannot answer.
Okay, I think we have to.
Your picture, there is a picture that you show the reconstruction. Can we go back to this picture? Before that, there was one more impressive before. Yes, this one. So there is a proof of uniqueness.
Yes.
I'm looking at this picture and I don't see the proof. I mean, the proof says that if I have sigma 1 equal to sigma 2, I mean, if the data is the same, I can get the conductivity right. But the conductivity here is different than the one that is on the.
So of course, when the R is infinite, so there's this mathematical question uniqueness, and that's when the R is low pass. There's no low pass filter. You have infinite conductivity, and then we can prove mathematically then you have uniqueness. But to use this proof to reconstruct, then you have to do this filtering, and then it produces this.
So maybe the real question we should ask is what's the distance, because if you have a distance between the data, which is very small, what's the distance between the solution?
Yeah, so we have a project with Samuli and others to build up a whole regularization procedure which proves and estimating how things are. But there are these stable results by Royce and others, so they show that there is some stability, like in this kind of geometries, like here.
Right. I guess